Hello everyone and welcome to the today's sessions of complex and conformal frequency selective surfaces-based Radome simulation. Thank you for taking time out and being here today. My name is Reza Hosseini. I'm application engineer at Dassault, and I'm so excited to talk about the Radome simulation workflow in the next roughly 45 minutes. So this slide is about a quick overview of what we expect to see and follow in this webinar. Basically, frequency selective surfaces, or FSS, are created based on a periodic structure that in fact show intrinsic electromagnetic phenomena. We talk briefly about it later in this webinar. And let's not forget that our goal is to design and simulate a Radome-based FSS. So this workflow shows that we start from a unit cell level, a single unit cell level, and then we can extend it for infinite array simulation. Then we go to planar finite array, and then we can go have a conformal structure, and then at the end, a realistic Radome based on the FSS structure that we designed. To have a summary, or let's say agenda of what cases that we're going to investigate in this study. So basically, there's a 5 cases, starting with the infinite array simulation. After that would be a planar finite array, which we consider 2 cases. The one case with a plane wave illumination as excitation, and the second one would be an antenna as excitation. Then we go to finite array, but in the domain of conformal, so it's not planar anymore. So we have a bended array or curved array, again with a plane wave and antenna, cylindrical array with a plane wave, and realistic radomes with the antenna inside that. So before starting and going to the cases, there's some slides at the beginning that I would like to draw your attention to. And one of them is about the different modeling approaches that we have, or we could have inside the CST to address the issues. So one could be for infinite size. So as I said, we could start with a single unit cell and create infinite array, and then perform Selective-mode analysis to find the transmission and reflections for infinite array. And then after that, we can have using the compact material modeling, or what we call it SIMPanel. Inside the CST, we can represent those behavior of infinite array using a SIMPanel material. And the second option, second approach is using using finite size. So the finite size, it could be planar, conformal, realistic, and then we can use the structure, the full detailed structures, or with all the details, the geometries that we have inside the CST, or modeling them with the SIMPanel material or compact material modeling that we have. So we're going through all of those cases in this webinar, starting with the infinite array simulations. So before getting into infinite array, I would like to have a quick overview in the Selective-mode analysis. So basically, when we have periodic structures, the phase relationship between the incoming wave and the diffracted or scattered waves it could be written based on the Bloch theorem. So when we have the wave vector of the incoming wave plus the periodicity of the structure in, let's say, the two directions. So as here is shown by gamma lambda 1 and lambda 2, so indicate the periodicity of in direction of first and second reciprocal lattice vectors. So and then based on this analysis, you can find what is the basically transmission and reflection for these infinite array and for several local modes. Yeah, so the model that I use in this investigation is pretty simple in a way that we have a dielectric, and inside the dielectric it is a circular metal. The frequency range of interest is between 10 to 25 gigahertz. So the quarter of wavelength inside the dielectric would be between 0.2 and 0.08 centimeter, and the thickness of the structure is around 0.05 centimeter, which is 6 times smaller than the minimum lambda of interest. The full wave solver that you use is transient solver, and we're going to talk about it later in detail. And you can also see the structure and the dimension of the unit cell. So as I said, start with the infinite array. So we can see using the Selective mode analysis, we can find the transmission and reflection. So here, what we see in the left and the right side, this is a reflection coefficient for that structure. It shows that at the frequency of 19.2 gigahertz, we have a sharp dip at the reflection, meaning that the field can pass from one side to another side, so it can go through the structure. So the structure is transparent at that frequency. This is what we see at the field animation here, and the frequency outside that range, which yeah, I call it notch band. This is a frequency that the field cannot get through the structure. So the structure is basically blocking the field. So these are fundamental frequencies pointed here we have, because we're going to address to these frequencies later. So this concept of passband and notchband, it is important here. The other important factor is that the transmission and reflection changes also with incident angle. So the previous slide, the field animation was there for the normal incident angle. But if you go in a parametric sweep over the different incident angle, we can notice that basically both magnitude and phase for reflection, so here we have it only reflection, but for transmission it's the same, will change. So that's a interesting effect, and that actually could affect our further simulation result, and that's something that we need to take it in consideration. So as we can see here, so from theta equal to 0, which is the normal incidence, going to 25 and going to 20 to 60 degree of incident angle, the frequency that the pass bands or transparency of the FSS is happening will shifting toward the lower frequency, and also the phase shift will be happening. So we can see here basically that this structure exhibits a strong dependency to the incident angle of incidence. So come back to the point that we had for compact material modeling. So next step after designing the infinite array is to simulate and characterize the finite size structure. But here is the point that the compact material modeling could be helpful in order to save computational resources in terms of simulation time and memory, particularly when the models get large and complicated. So therefore, cPanel materials helps to have these options. So so this slide shows where we can find them and what types of them exist in the CST. And yeah, here, so inside the material, we have a cPanel, and there's basically 3 types of the cPanel exist. So we can have a stack up, which here is also showing in which solvers they are will be supported in which solvers. Stack up mode, which is working for normal incidence. We have a reflection and transmission table, which is for angle-dependent definitions, and it could be angular-dependent in asymptotic solver, and S-matrix, which is also for single incident angle only, so it's working for one angle. So short overview what I mean by stack up layers. So basically, if we have a multi-layer materials together, so we can, if the some certain conditions, such as that the thickness of these material together are not comparable to compared to wavelengths or small. And considering of the plane wave conditions, so we can represent that material with overall transmission matrix over infinitely small and thin sheet. Second option that is important to mention, that was the option that we had for a reflection and transmission table, and that option is only supporting asymptotic solver, and it's important because here we could have this dependency over the different incident angles. So unlike the other two modes that we have, there's no limitation in terms of incident angle. It could be for normal or for any incident angle, and for two different polarization for the plane wave. And I may emphasize on that because I'm using this one later in this webinar. And comment more about why incident angle is important. Here we can see that when the plane wave is heating, imagine that this is representing our finite size curved structure. And then the plane wave, when it's coming from, let's say, the upward down. So it's a different point at these radome, at these structures, would be creating different incident angles. If it's at this center point, it would be exactly normal. But the more we get at the other points of the radome, there would be other incident angles. So, and that is important if our FSS is angular dependent. So if it's not angle dependent, that's fine. So well, we should not, we can just forget that. But if it's the angular dependent, if the characterization that we do based on the infinite array shows us that the radome has some strong dependency to angle of incidence, so this is something we should consider. So how much that could affect a result. And equivalently, we can see the same concept in using antenna as a source instead of plane wave illumination. If the antenna stays in a focal point and sends rays normal to the surface of the radome, there's no much difference between a stack-up type or angular dependent type, because we do not have in that case that much angular dependency. But if the antenna stays, let's say in this case, out of a focal point, so the rays or the field, the propagation vector of the field when it comes to the radomes are experiencing different angle of incidence. So in that case, there would be different between the same panel modeling that we would use. So this is our effect that we will show later in our webinar. So, so therefore, it is also important to see if the radome, if the FSS is angular dependent or not, and then we should consider that for our further material modeling. Right. So basically, this slide would be a conclusion. In fact, I brought it at the end, but before getting into the different cases, I want to bring it here to give you a heads up what you would expect to see at the end. So basically, we can combine or divide basically the simulation approach in solver and model, and the dependency on incident angle or not. So if we have a full wave solver, by full wave here I mean transient solver, but it could be our frequency domain solver as well, or integral solver. So basically all the full wave, but I here used transient solver. So full structure, I mean that we do not have any let's say approximation in terms of material modeling. So we do not use SIM panel. So we actually generate the whole structure that we want. So So in that case, yeah, I mean, we'll be simulating the full model, so there would be no limitation or constraint in terms of result or accuracy of the result. When we're using the full wave and SimPanel with the stack up or its matrix, it is the red color means that we need to take care. We need to be thinking cautious about the result of the simulation when the dependency on incident angle is there. The third option that I considered in this investigation is about the hybrid solver, which I'm going to talk later. So basically between a transient and asymptotic solver, and then the sim panel defined in asymptotic solver where we could have a table for different angle. And in that case, that problem of dependency incident angle could be solved. The antenna model that I used in cases that I had antenna as excitation, I used the inverter F antenna with a resonant frequency at 19.5 gigahertz, so more or less at the same frequency that our FSS would be transparent and with almost is homogeneously isotropic radiation. So before getting to the cases that I earlier mentioned, I did a sanity check. So I made a curved, let's say radome, curved structure with only one and then dielectric layers with the antennas. You can see that this point is small, and then I represented the same basically radome with the equivalent sim panel definition of that. So basically, and then I wanted to see that if it's just simple dielectric, how would that work? So I expect that everything to be okay, and we can see that basically the return loss and the electric field probes they're pretty the same. The far field also pretty much the same, and also the field visualization at 19.2 this similar frequency, they are exhibiting the same behavior. So far so good. So let's start with the cases we had. So after solving the infinite array and seeing how our infinite structure would work, we want to have the finite array, because at the end the radome would be finite. So as I said, so we can do two cases in parallel. This is always the case I've done. So first would be the full structure, so the structure with the real geometry, and then the second would be represented by sim panel. And in this case, I'm using plane wave as in excitation, and the plane wave is hitting the surface of the structure with the angle of theta. And one way to characterize this sort of finite size array is to using RCS probe. This is a probe that we have in our transient solvers. So it could be defined in the far field and in the spherical coordinate based. So that's why if you have a theta comes here, we can have also theta equal angles scattered or reflected back, and then we can sense the field there. Of course, we can also use the full far field monitor to see how the overall behavior of the far field result would look like. So getting into the simulation results, so here is brought four different incident angles. So starting with the theta zero, so basically normal incidence, and we can see that the result between the full model and the sim panel representation are pretty much the same, because as I said, this is a normal incidence, we expect that, but the more we get in the angles that are deviate from the normal incidence, for example, theta 30 and theta 60, and yeah, also theta 75, we can see that deviation starts to be bigger and bigger. So, and always having a two sort of line to compare them. So one is pass band, one is notch band, and we can see that the major different by increasing the angle comes at the pass band. So it is first it shifts, although the notch band starts to be more, it would stay a bit the same unless that we go quite high in the angle, and then that would be quite different. So the same concept, the same result, but using the full far-field monitor. So previous one we just showing at one certain point with the RCS probe, but now we have it in a full 3D monitor. So you could see that for it at 0, so the normal incident angle. So this one, this column on the left is representing F frequency equal to 15 gigahertz and notch band, let's say, and the right column is for the 19.2 gigahertz, which is our pass band. And then always is comparison between a complete model, I mean the full geometry, versus SIMPanel, and for different angles. So for the theta equal to 0, we can see that pretty much the same. We are in the notch band, and then for theta equal to 30, still the same. And theta is equal to 60, we can see that the notch band is still more or less remains the same, but it's not the case when we go into pass band. So, and see the reflections will be different in terms of value and also in terms of the side lobes, and the same things for theta equal to 60 degree. So it was a planar array. So let's say we want to see how it look like if we go into the curved radome. So here, this is the curved radome with a, let's say, a span of almost 20 centimeter. This is also using plane wave again. So the same concept. Basically, we will consider different angle of incidence and monitoring the probe for the RCS, the far field probe at the distance, and compare it between the full geometry versus the SIMPanel representation. And here it's the difference that we can see, that even at theta equal to 0, that the difference are observable. So if you could remember for the planar one that we just showed a couple of slides ago, so they were pretty much the same. But when it comes to the curved structure, we see that this red line, which is the solid, the full geometry, is not it's not very well on the SIMPanel. So the SIMPanel remained the same, but the full geometry is not following that much anymore. So the difference starts to appear, and also for the different angles, so we can see different behavior. The same result for using the full far field monitor. So we have in the left columns notch band for 15 gigahertz. In the right columns, we have it for 19.2, and then between complete full geometry in the SIMPanel representation and for different angles. So you see that's lots of information. I hope that you could follow the point. So here for different angles for the notch band, the result is pretty much the same, not that different, although there are small differences. But when we compare it to the pass band, we can see that the SIMPanel results are quite different from what we get from the full geometry. So and to be again looking at from another aspect, so I'm here showing the electric field visualization at the passband frequency for theta equal to 60 degree, the incident angle of 60 degree for full geometry versus SIMPanel. So you can see that here, when the field at the 60 degree would be almost in this arrow, let's say, direction. So when it comes to the radome and it hits the radome here, almost normal, it can pass, because this is what we expect to happen. So we need to expect the field passes. But when it comes at these points, which is not exactly let's say 90 exactly normal, so we can see that there would be another patterns, and there is some sort of deviation in the field happens. But when you look at the sim panel, that's yeah, it passes all, so it doesn't see the difference of the incident angle. Yeah, so another test is the planar radome using antenna as a source. So comparing to the plane wave that we have antenna, and we can see here that with electric field visualization, so basically with the electric field, that there's a substantial difference between what we get from the full geometry versus sim panel. So basically sim panel, again, as I said, it cannot distinguish in this case, because we're using the sim panel in the transient solver, it cannot distinguish between different incident angles. So it just sees the normal incidence. And here we would have some standing wave patterns because the field reaches to the radome the different angles, and then they would be reflected back, and they're creating the standing patterns. Yeah, we can compare the result with the far field comparisons in that case, and yeah, we can see that the result with the sim panel, so this blue curve, it's is different. So there is some deviation that they cannot follow. Some certain angles, some certain let's say degree cannot follow the full geometry. Yeah. So another case is curved FSS-based radome. So the same as before, but instead of using the plane wave, we use the antenna as an excitation, and comparing between solid model and sim panel represented model. So so here is the point that I wanted to show you what was the solver I'm using. So it's a solver, transient full wave solver. But inside the transient solver, we have basically two solver. One is a standard transient solver, or FIT, finite integration technique, and the second one is a TLM solver. And the reason I'm using TLM solver is that with the help of the lumping the mesh, as you can see here in the structure, so we can reduce the number of mesh quite a lot. And especially in this case, because we're dealing with the larger structures and between the radomes and the antenna, basically there's not that much geometry there, so we can save some mesh there. So that's help quite a lot. So that's why I'm using the TLM for sake of this presentation. So comparing the case of the electric field for this case, for the curved radome with antenna as a excitation. So here is two frequency that these are, let's say, they are out of the band, out of the transparency band of the FSS, and we can see here that so basically there is three different comparison. From left, it would be full detailed structure, so full geometry in the TLM solver. Then we would have sim panel stack up representation in the TLM, and the third would be sim panel, but in asymptotic solver with the help of hybrid solver. So the hybrid solver that is between TLM and asymptotic solver. I'm going to talk in a second about it. And here also another frequency, notch band frequency. So what we can see is that the results are pretty much the same between these three approaches, because as I said, we are not in the range for let's say transparency of the FSS. But when we look at the 19.2 gigahertz, which was the frequency that the FSS was transparent, and we can see that the significant difference between, let's say, sim panel stack up model compared to the other two. So basically on the left, we have a full geometry. And so let's say we keep it as a reference point because it's a full geometry simulation. And here in the middle, there is a full wave with the sim panel representation in TLM. And on the right side, we have the hybrid solver with the angular dependent sim panel definition. So here we could see that the result here on the right is quite similar to what we get at the left with the full model, full geometry, full wave. And basically these standing wave behavior inside the area of the radomes are more or less the same are being created, while the SIM panel, the TLM SIL panel, the stack-up SIM panel cannot see that. So basically, it's again, this is a major difference where we go to because it comes to the point that the angle of incidence getting important. So how we do the hybrid solver. So this is the slide about how I've done that. So basically, it's and it comes from the name. So we are combining two different solver to get basically tackle these electrically large structure. So we're simulating the antenna with the help of the transient solver, TLM in this case, and we using the capturing the fields, monitoring that and recording that with the help of the near field source, and bring it back inside the asymptotic solver and replacing that antenna with the near field source, and we do simulation, and then we get the results and bring it back to the antenna, and then and we're going through this iteration until the point that the residual error of the simulation getting of a certain degree of threshold that we set initially, and then the result can be trusted. So here is the table, the screenshot of the table that we use with the different frequency and different angles to properly, let's say, characterize the behavior of the DFSS with the help of the SIM panel. And then there's a comparison between the return loss between these three different methods we have. I So here's the far field comparison. So basically the same result as the previous one we showed in the electric field, but here we're showing in the far field mode. So we can see that there is some certain discrepancies between three methods. So the point is that the full model and full geometry should be seen as a reference, and then if we look at the others two, we can see mainly that the hybrid solvers can follow the reference, and the SIM panel one, the SIM panel stack up will be the after that. So this is some point is good, but not all the time. So we are increasing the, let's say, the complexity. So after the planar and curved structure, we go to full cylindrical curved FSS. So in that case, I just use the plane wave because it has a symmetry, and so we do not need even to sweep the incident angle of incidence. The one angle of incidence, the normal, could work. It consider all the angles automatically. So due to transmission in different frequencies depending on the angle of incidence, so we expect to see some standing waves behavior inside the cylinder. So here should be sort of cavity behavior. So this is, I call it extreme case, because this is a case that all the angles are happening at the same time. So this shows the capability of an applicability of each approach. Again, here's a screenshot of how basically TLM solver and TLM mesh could be significant help in terms of calculation. So you can see here that we're saving lots of mesh inside the cylinder. Well, basically there's just air, so the geometry in the edges, and we do a better meshing there. So I think I have two slides here to compare the results. This is a field amplitude, and as before, the left side, the full detail structure, SIM panel with the help of S matrix or stack up, and here we have the hybrid solver sorry, here is a only asymptotic solver with the definition of the angular frequency dependent. So here's a frequency of 8.42, which is a notch band again. So here we see that the yeah the pattern, the field amplitude is, we can say, is more or less the same, but it would be quite different if you look at the 19.4 gigahertz, where the transparency of the FSS is happening. So in that case, we can see that, as I said, we're expecting some cavity behavior, we're expecting some standing wave behavior inside the cylindric, and the full detail structures shows us that one to us with some certain of the surface resonances as well. And the asymptotic solver is also showing up to some certain degree, but the SIM panel with the S matrix basically does not show us that much. It's like, as I said, so the field is coming and getting through, and those, let's say, cavity behavior is not there. um, um, to go a bit more deeper, so I used the electric field probe at the center of the cylinder and trying to monitor the electric field behavior over the frequency range of interest between, and compare them between the different methods. So we can see here that the these three or these four basically curves, they're more or less following each other, and the only difference happens at this frequency range, which if we zoom in more, we can see that at around, let's say, 19, 18 gigahertz, where again this transparency is happening. The green curve is a bit off from the others, so basically it does not follow, and that's again, if you look at the green curve, it's the SIM panel. So the SIM panel in TLM, which is the stack up way, which is the symmetric definition, and the point is that it cannot see the angular dependency. But it's quite interesting to see that the asymptotic solver, although it's not a full wave solver, it's only asymptotic. So there's some certain of approximation inherently inside this algorithm. But we can see that it's pretty much with the help of this SIM panel, it can follow the, let's say, the red curve, which is the full model, full geometry. So followed very well, and then the result would be even better if the number of rays that we considered increase. So here you can see from 3 rays to 15 rays, it would be it can follow the sharps better. Last and but certainly not least, we are going to Conformal FSS Radome. Let's say I call it realistic design. So this is a cone shape Radome. And so basically we used our idea of FSS and we wrapped that surface along around a cone-based shape, and inside that we will have our slotted array of waveguide to work as an antenna, as a source. And there's basically two approach. One approach is a solid, is a full geometry, and the other one is the representation of that with the help of SIM panel. And you can see here the dimensions is a 0.5 meter, so, and 25 centimeter it's width of the openness of the cone. So you can see that the structure it is pretty large in terms of electric, and we were talking about 25 gigahertz, the highest frequency. So again, that's why I like to use the Conformal, sorry, the TLM mesh. So here you can see that how the TLM helped me. So reaching from the initial number of mesh of 1.3 billion to down to somewhere around 72 million. So you can see here that the mesh are wrapped more around the structure, so better, finer mesh here, and then away from that we can relax the mesh a bit. So I used 2 GPU card of a Tesla K80 to have a hardware acceleration, and so this antenna array has 10 port, and there was a transient solver, so almost I needed 4 hours per each port to get the full result. So here to compare the behavior, so at the top is the result, the far field result of the radome at the frequency of 19.4 is basically the passband, and this is the full detailed structure. In the bottom we can see the SIM panel with stack up. Like the previous, like the curved radome, also used here the hybrid solver approach as well. So where that we basically, with the help of communicating between the near field source and the asymptotic solver and going through iterative way, we're bringing the overall error quite down. And then we get the let's say the far field from that way, and then this slide bring them all together so to have a better overview. So we can see that at the passband frequency for the, let's say, the main beam, they are more or less they're doing well. Although looking at the full geometry model in top, so we see there's some quite spiky, let's say, sharp side lobes and a bit stronger back lobe. That these are cannot be seen in the SIM panel, and also in the hybrid solver. So as I said, so this is a reference point, but we can compare to the other two, and to see how much gain we can get from using this help of these tools. Yeah, bring it here again. The another comparison between the far field pattern, these three different methods. Yeah, so at some point they are following at some certain angles, but when it comes to, let's say, the back lobes, there's a difference. So basically the SIM panel definition in the back lobe in this case could not see the full detailed, let's say, geometry. And for this frequency, they are, yeah, a bit better. Basically, they are okay. Actually, they are following very well. Yeah, so let's look at the electric field animation of the radome. So if you're looking at the passband, so this is the full model with the antenna. So the antenna starts radiates, the field reach the radomes, and they are getting out of the radome. But if you're looking at the notch band, so either at 25 gigahertz or 15 gigahertz, we see that the radiation of the antenna cannot get out of the radome. So they are pretty much damped. So you can see, and the scale of all the fields are the same. So you could see here the field literally getting out, but here it cannot. And also here is pretty much damped. So, and looking at the same behavior with the help of the SIM panel, SIM panel, let's say asymmetrics in time domain solver, you can see here in the passband there is a clear moving out of the radomes, but also in the notch band the behavior is a bit yeah, let's say the fields can get a bit more out of the radomes compared to the full details. And again, the scaling are the same, so basically we should be able to judge with the colors. So here yeah, basically we are a notch band, so the fields should not get out, but here in this case there's a bit also field can go out. So that brings me to the conclusion slide. So this is The slide I showed earlier in this webinar at the beginning before we getting into the cases. So if we divide the approaches and the simulation case in full wave and in the solver and the model, so we can see if you have a full wave and full structure, so basically we are in the complete range, complete set, so no problem. Using the full wave solver in the sim panel as a matter of a compact material modeling to help us to have a, let's say, faster and more efficient simulation would be fine if it's a no dependency on incident angle. But if it's dependent on incident angle, we need to be cautious. And using a hybrid solver, basically using asymptotic solver as a solver that can help us to simulate the behavior radome, and then in that we model the radome with the help of the sim panel in the asymptotic solver, which is the table with the angular dependent and frequency dependent behavior. So then we're good to go for no dependency and also dependency, because the table is angular dependent.